The conservation of momentum is a highly useful tool in the scientist's toolbox. Good acronym, instead of having to write out the whole thing, conservation of momentum. And it says that if a system is not subjected to any external forces, then the total momentum of the system is conserved. Phew. All right. So let's take a look at a simple example. We'll have an initial and a final case. Now let's suppose that we have two objects in motion. Object M1, object M2. And they're moving along with velocities that are going to allow them to collide. So M1 is moving with velocity V1, that's the initial value. M2 is moving with velocity V2, that's its initial value. They collide and then they bounce off of each other. And let's see, I don't know exactly what's going to happen, but let's suppose the M1 now is going in this direction, and that'll be the V1 final. And the M2 has bounced off and it's going this direction. And that will be its final value for the velocity. Well, the total momentum is going to be conserved according to this statement up above, if there aren't any external forces acting on the system. There are internal forces. When the two objects collide, they're exerting forces on each other. So internal forces are allowed, but nothing can come in from the outside. So in particular, with this example, not made clear at all, if we're doing this in the air, where gravity is trying to pull the objects down, this isn't going to work. Maybe these objects are way out in space, far away from everything. Nevertheless, conservation of momentum tells us the total momentum initial is going to equal the total momentum final, but with the two objects, that's going to be the P1 initial. Total momentum in this case is a total in a vector sense. So the momentum of object 1 plus the momentum of object 2, the vector quantities, that'll be the total momentum. And it's going to equal the total momentum final. So the momentum of object 1 final plus the momentum of object 2 final. Momentum, of course, is mass times velocity, so immediately we can translate this into the mass times velocity of object 1 initial plus the mass, that was mass object 1, mass of object 2, the velocity of V2 initial, and that's going to equal the mass of object 1 times the velocity of object 1 final plus the mass of object 2 times the velocity of object 2 final. Excellent. Depends on the problem, but if the objects collide, bounce off of each other, no external forces are present, this equation is going to be valid. And that is just the conservation of momentum. There's a specific case, though, where the objects collide, but they don't bounce off of each other. In fact, they stick together. So let's take a look at that and see what happens. In fact, let's go ahead and transition over to a one-dimensional problem. That way we don't have to worry about gravity if the objects are moving in the horizontal. We'll do it with the initial and the final again. And we could have object 1. I'm not going to draw the surface. These could be cars on the road. It's just they're moving in the horizontal. Often think of collisions as having objects coming together, so we'll let those two objects collide. But what makes this case special is that when they collide, they stick together. So it could be two pieces of putty that collide and stick together. Could be two train cars that collide and stick together. Whatever the case, it's a special situation. Let's suppose that they collide, stick together, and then they move off together. I don't know without more detail whether they're going to move to the left or to the right, or in a very certain case, they would just stop altogether. This is going to be a little more symbolic than that. So we have objects 1 and 2, M1 and M2, with their velocities. This will be V1 initial and V2 initial. Those are the speeds, but the directions of the arrows complete the idea of having a velocity. And when the objects stick together, we could say that this mass is M3, and they're going to move off together with velocity 3, and this is going to be the final velocity for the system. But it turns out with the objects sticking together, really the M3 is just going to be the sum of the individual masses. So M3 is M1 plus M2. The conservation of momentum is a vector equation. So here in the horizontal, we need to look at the x components. And we'll have, this kind of goes overboard on the subscript, sorry about that, but we'll have M1 times the V1 x component initial plus the M2 V2 x component initial. It's going to equal the M3 V3 x component final. Or then finally, repeating the left-hand side, and just acknowledging the fact that the M3 is really the same as the M1 plus the M2. In this case, where the objects stick together, it's given a special name. This is a perfectly inelastic collision. And it seems to occur often enough that rather than writing out the full terminology there, it's a lot easier to call this a pick. So anytime two objects collide and stick together, that's a perfectly inelastic collision. And here in the horizontal case, as written out there, we have this example of the conservation of momentum.